Bismillahirrahmanirrahim, students. We are starting our lecture about the concentration of electrons and holes in a semiconductor. So our previous lectures are about the introduction of semiconductors, types of semiconductors, how you can differentiate between intrinsic and extrinsic semiconductors. So now we are at the point that how many electrons per unit volume are there in the conduction band, or how many holes per unit volume are there in the valence band. So how we can estimate about their concentrations and on what factors these concentration can depend. So first of all, we'll start our discussion. So if you memorize the topic of density of state, in which you have calculated the number of electrons in any metal, like you studied in the previous chapter. So similarly, we have to find the density of states of electrons in the conduction band, and we have to find the density of states of the holes in the conduction band. So we have a relationship for the density of state of the electrons which are existing in the conduction band. This is the relationship per unit volume, which depends upon the difference of E minus EC square root. And this is a relationship for the density of state of the holes. Density of state of the holes per unit volume also depends upon the square root of EV, energy of top of the valence band, minus E, energy of the hole. And here EC is the energy of bottom of the conduction band. So to find the number of electrons or number of holes per unit volume in conduction and valence band respectively, we need probability function. So probability function is also well known to us. The probability function to find electron is f of E is equal to 1 over 1 plus exponential E minus E over kb. If you want to find the probability function for the holes, it means that not electrons. So overall the probability is 1. If you minus the probability function of electron from 1, then you get the probability function for the hole. So that is the procedure we have done. So for the holes, we use subscript P, and for electron we use subscript N. So we get 1 minus probability function for the electrons will be equal to the probability function for the hole. And if you simplify it, then you simply get 1 over 1 plus exponential EF minus E over KBT. Very simple calculation it is. So everyone of you can easily. So you have density of state and you have probability function for both electrons as well as for the holes. So for any given energy range D, you can easily find by multiplying this probability function with that of the density of state in the energy range D. And if you want to find out through the whole band, then you have to integrate to find the concentration of electrons in the conduction band or concentration of holes in the valence band. The better description of the variation of density of state for both electrons and holes is represented over there. This is the top of the valence band EV. This is the bottom of the conduction band EC. So both density of states depend upon square root of delta E minus EC and EV minus E. Okay. So this difference depends upon which one is greater. EV is greater, you know that in the valence band, and E is greater in the conduction band for the electrons. So the trend is like this, as you can see this blue color, like this. With the increase in density, the energy of the electron increases. Right? So this is the trend of density of state versus energy curve. which in return give us the concentration of electrons and holes in the conduction or in the valence band. So, we come back toward the mathematical description of it. So, dN naught, concentration of electrons in the energy range dE is equal to F of E is equal to F of E, Sc of E. Sc is for the density. Over there, this we use for the density of state of the electrons, and D is the energy interval. So, by substituting the values of Sc of E and F of E, you get this relationship, right? You simply put the values. So, over there, this delta E minus EC of forbidden gap is of the order of 1 electron volt for the semiconductors, and the KBT is about 0.025 electron volt. So, the exponential term in the denominator, this one, is basically very, very greater than 1. So, it does not matter much if you add 1 in the denominator or not. So, you can ignore this one. So, this distribution change from Fermi to Maxwell distribution. And it actually does not have any significant effect on the outcome of the probability function. So, you simply remove 1 from the denominator over there from here. So, you get dN naught at any given temperature, number of electrons that are present in the conduction band. Right? Here EF is Fermi energy, E is instantaneous energy of any given electron, and EC is the bottom of the conduction band, and EV is the top of the valence band. So, you have to keep in mind all these terms. Sc of E is basically density of state of the electron in the conduction band, and Sv of E will be density of state of holes in the valence band. And to indicate electrons, we use subscript N, and to indicate holes, we use subscript E. Okay, so after this simplification, due to large exponential term in the denominator, we eliminate this one. All of the steps are quite simple and mathematical. So, to find total number of electrons per unit volume, you have to integrate it. Okay, so from where to where? So, you are dealing with conduction band. So, you start from bottom of the conduction band. So, you start from EC, and it can go up to infinity. Okay, so it should practically go up to top of the valence, top of the conduction band, not infinity. Right? E minus AC is square root exponential this minus E over KBT dt. Here you add exponential EC minus AC over KBT, which is also equal to 1. So, it can be written like this. So, you have to write all these two values. So, minus EC is there and plus EC is there inside the integral. Okay, so this is a simple integral. To solve it, you have to change the limits. So, we use substitution method to solve this integral. So, we put E minus EC over KBT is equal to XC. E minus EC is equal to XC KBT, and DE is equal to KBT dx. Okay. So, we use limit when E is equal to EC. Okay, put over there E is equal to EC, then this will be EC minus EC. So, XC will become 0. And for E is equal to infinity, XC will also be equal to infinity. So, making this substitution in the next slide. So, this was your original equation, and these are from the substitution. Okay, so N naught, you put all these values using these terms. You replace E minus EC with XC KBT over there, and you have taken all the constant value outside XC KBT. Okay, you replace D by KBT dxc, this one, and you replace EC minus E over KBT by F. Okay, just simplify it, you get, you will come to the conclusion or the final result of N naught. You get N naught is equal to NC exponential EC minus EF over KBT. Here NC is a common name of two terms which are written over there. NC is equal to 2 into 2 pi M square KBT over SKF whole power 3 by 2. Okay, so this N naught gives you the concentration of electrons at any given time. So if you see this, you have two terms. One is this exponential part and other is NC. So it is very clear over there that on what factors this concentration will depend. On what factors this concentration will depend. So in that case, you can see EC, energy of bottom of the conduction band, Fermi energy of the material, and temperature of the material. Okay, and over there you can see this NC is proportional to temperature power 3 by 2. So there is a clear dependence of concentration of electron on the temperature, on the Fermi energy, and on the energy of the conduction band. So this equation gives you the number of electrons per unit volume in the conduction band of the semiconductor, which is also called concentration of electrons. This is true for both intrinsic or extrinsic semiconductors. Because it only changed the Fermi level, the only clear difference between intrinsic and extrinsic semiconductor occur is change in their Fermi level. So the formula can be effectively implemented for both intrinsic as well as extrinsic semiconductors. The all process you have done for the electron can also be repeated to find the concentration of holes inside the valence band. So you keep in mind the major concept. You are finding concentration of electrons in the conduction band, and you are finding concentration of holes in the valence band, right? So holes are existing over there in the valence band, and electrons which are take part in the conduction, they exist in the conduction band. So again, we already know the SV of P, density of state of holes inside the valence band, this subscript V for the valence band, and this probability function Fp of E, which we also calculate on the first slide. So put the value of SV of E and Fp of E from the first slide, you get dP naught, the concentration of electron per unit volume in the energy range dE. Okay, so again, changing the approximation for EF is greater than E, you know, because the hole lies inside the valence band. And KBT is, you know, 0.025, so denominator has a larger exponential term as compared to 1, so 1 can be eliminated. This is all we have already discussed in the case of electrons. So all the steps are same. So again, you introduce these terms over there. So minus EV over KBT is combined over there. This is equal. This is equal. So powers are added, and this is all presented over there. This is plus EV, and this is minus EV. Okay. So to find the total number of holes inside the valence band, you have to integrate this for the whole valence band. So the valence band starts from minus infinity and it goes up to EV, top of the valence band, up to top of the valence band. This will be the limit of the integration. So simply integrate the above equation. These constants are outside the integral, so integral is minus infinity to EV minus E over 1 by 2 exponential this. Okay, so Process is quite simple. The same substitution will occur. XV is equal to EV minus E over KBT, and EV minus E is equal to this, and D can be written like this. It's very simple mathematics. So if E is equal to minus infinity, okay, you put it over there minus infinity, then XV will be equal to infinity. So the limit change to infinity, and when E is equal to EV, if you put EV over there, then this will become 0. So XV becomes 0. So your limits change from infinity to 0 over there. These are the limits from infinity to 0, and put the values from these three equations over there. So your integral change change its form. It's changed from d to dx form, and all the calculations are now quite simple. So just simplify it, you will get the concentration of holes, which is equal to NV exponential minus EF minus EV over KBT. Here EF is Fermi energy, EV is energy of top of the valence band, and KBT, KB is Boltzmann constant, where T is the temperature. So this P naught is the required number of holes per unit volume in the valence band of a semiconductor. So this is also true for both as well as intrinsic as well as extrinsic semiconductors. Again, the dependencies are same on the temperature as that of the electrons. And one more thing is very common to know, that for an intrinsic semiconductor, number of holes and number of electrons are usually same. That is the reason the probability function was actually very similar to each other. So you can see again, I have pointed out over there the dependence on the temperature. So both concentration of electrons as well as concentration of holes depends upon T power 3 by 2 and exponential minus 1 over KBT is the term on which the temperature dependence is very clear, and you can also verify that this is KBT in the denominator of the exponential, and over there this is T power 3 by 2 part, which is in the N.Sc, which lies in the N.Sc. Same is observed for the holes. So you can see this exponential power minus 1 over KBT, right? And this part show you the dependence of number of holes on the temperature power 3 by 2 cube root of the temperature. So this is how you have both the concentrations for the electron as well as concentration of the holes. So this is our discussion for today. Hopefully you have understood it. So thank you for your interest in the lecture. So if you have any question, you can ask. Thank you for your patience. No, your mics are open for the question. So if there is any question, you can ask. Yes. If anyone want to ask any question.
सर ऊपर एक क्वेश्चन में सेकंड स्टेप नहीं समझ आया, वो बता दें पीछे जी यहाँ पे।
जी सर।
यस सर।
ये आपके पास देखें, आपने Xc को पुट किया है EV माइनस E और KBT, राइट। नेक्स्ट स्टेप में आपने KBT को मल्टीप्लाई कर दिया दूसरी साइड पे, ये बन गया XV KBT इज इक्वल टू EV माइनस E। फिर आपने इसका डिफरेंशियल ले लिया। अगर आप मेरे पॉइंटर को देखते जाएं तो मैं इक्वेशन बदलता जा रहा हूँ। ठीक है, तो ये सारी चीजें इक्वेशन में मौजूद हैं। ऊपर जो पिछली स्लाइड में आप इक्वेशन देखें, दिस वन, ये EV माइनस E मौजूद है, ये एक्सपोनेंशियल में E माइनस EV और KBT मौजूद है। तो जहाँ जहाँ ये टर्म मौजूद हैं वो इस लाइन के हिसाब से जो आपने इसकी नई लिमिट्स एवेल्यूएट की, वो आपने जो सब्स्टिट्यूट की इस इक्वेशन के, उसके बाद आपने सिंपली
सर KT जो KT की पावर है 1/2 वो कहाँ गया, उसकी समझ नहीं आ रही।
इंटीग्रल लेके ना आप किस चीज का आप इसको तसल्ली से सॉल्व कीजिएगा, ये दैट इज क्वाइट सिंपल, आप आसानी से कर लेंगे।
जी
सर जो आपने KBT पोर्ट कि 0.025, तो उसमें बोल्ट्जमैन कांस्टेंट की वैल्यू आ गई 1.38 का स्टैंडर्ड। तो टीएस में सर टेम्परेचर कितना लिया है आपने?
रूम टेम्परेचर पे बात कर रहे हैं
रूम टेम्परेचर सर?
जी। यूनिट यहाँ साथ मेंशन इलेक्ट्रॉन वोल्ट में किया है इसको, जब आप इलेक्ट्रॉन वोल्ट में कन्वर्ट करेंगे तो तकरीबन यही इसका आंसर है।
ठीक है सर।
जी, एनी अदर क्वेश्चन? Okay, thank you students for your interest. This is all from today's lecture. Thank you for joining. Allah Hafiz.